This brings us to the idea of mathematical models. Most concepts in physical science can be thought of as predictable relationships between quantitatively measurable properties. The most efficient way then to talk about these predictable relationships between measurable properties turns out to be through the language of mathematics. Most of the math that you learn in math classes was not invented by mathematicians. It was invented by scientists who needed tools to be able to express their ideas and make predictions based on what they knew. We're going to focus on two kinds of relationships that are very useful in science. One is called directly proportional relationships, and the second one is called inversely proportional relationships. In directly proportional relationships, we have the idea that as one variable increases by a fixed amount, the other variable, the related variable, also changes by a fixed amount. So if I have a graph of this phenomenon, let's say I have variable A here and variable B here. Maybe variable A is how much time has elapsed, and variable B is how far away is my dog as it runs. As more time elapsed, if my dog is running away from me, the distance that my dog gets away from me gets bigger. As this variable changes, so does this one. If this is a directly proportional relationship, that means every increment of time results in the same increment of distance. A changes directly with B. The mathematical relationship that describes this kind of a relationship is a straight line, and we all know that the equation of a straight line is y equals mx plus b, and so we can use that math to describe these kinds of relationships. The ratio that describes the relationship between these two objects is the slope of the line, and so slopes of lines are very often intensive measurable quantities. Density is an example of that. Density is a slope of a line that relates mass and volume. Let's look at this example. 60 miles per hour, that means that's divided by, that's a ratio between two variables. Think about an object that's moving at 60 miles per hour. First hour, it's gone 60 miles. Second hour, goes 60 more miles, so it's at 120. Third hour, 180. Fourth hour, 240. Fifth hour, 300. Every change in time gives me a corresponding equal change in distance if I'm moving at constant speed. And so I have the equation of a line. And the slope of that line, well, that's the speed. So you graph hours versus miles, and the slope of the line is speed. Let's say we had a different situation. Let's say we were going to start 10 miles from home and then go 60 miles an hour. So initially, at the beginning, we'd be like here. We'd be 10 miles from home, not at 0. Well, after some time had elapsed, we'd be at 70 after the first hour, 130, 190, 250, 310. Well, we'd still have the same slope because we're going the same speed. Slope in this graph is speed. Y in this graph is distance, miles. X in this graph is hours. Slope is speed. The y-intercept, well, that's just where were we when we started, really, and that's 10 miles. So the equation of this line is, remember, the equation of a general line is y equals mx plus b, where b is y-intercept and m is slope. Y really here is graphing distance. M is really speed or velocity. Time is x, and then b is 10. Or with units, the distance that you cover is 60 miles per hour times the time plus 10 miles. So that equation, that's not just this abstract thing from a math class. Equations of lines are useful tools for describing and predicting physical quantities. In the first graph that we had, where we started at 0 and went up, the equation of the line was much simpler. Y equals mx plus b, but if b equals 0, if you started out at 0, 0, then y simplifies to just mx. And when that happens, the math needed to make predictions gets a lot simpler. And so scientists get pretty revved up about finding relationships that have these sorts of graphs. That Kelvin scale we talked about earlier, that's why that happened, is to make this occur. The reason that this is good news to find a relationship that looks like this is because these sorts of patterns can easily be solved by using cross multiplication. Here's why. If we do a little algebra, we find that m, if we isolate the slope, is equal to y divided by x. And as long as you're on that line, the slope doesn't change ever. And so that means y at one case over x at that same case, for like point number 1 here, would have the same ratio of y to x at point number 2, a different place on the line. So that means the ratio of y2 to x2 is equal to the ratio of y1 to x1. And these kinds of problems, you can use the simple cross multiplication technique that you all learned in junior high to solve it. y1 times x2 equals y2 times x1. So here are the rules. How to know if you can use one of those simple cross multiplying proportions. The first thing that has to happen is the relationship has to be linear. What that means is it has to have constant slope. If you think about the graph of some relationship, if it goes like this, you could possibly use a simple proportion. If it's going like this, and it's all curvy, you cannot do that because you can't count on slope always being the same. The second thing is when one of the variables is 0, the other variable also has to be 0. So you can't have a straight line that has a non-zero y-intercept. But if the straight line goes through 0, 0, well, then you can. Now you don't always have to graph these out to know if you can use a simple proportion. Here's an example. Say you have a 1,320-foot roll of barbed wire. That's the length of rolls of barbed wire. And it weighs 78 pounds. Say you have a partial roll of barbed wire. Some of it's gone. It only weighs 43 pounds. And you wanted to know what the length of the wire was that remained on the roll. Well, every foot weighs the same amount, so that means it's linear. And if you didn't have any feet, well, it wouldn't weigh anything. So that means the graph of weight versus feet does go through 0, 0, and it's consistent. It's linear. So that means I can use a simple proportion like this. 1,320 feet is to 78 pounds as x feet is to 43 pounds. Now I'm going to cross multiply and divide to find my answer. That means 43 times 1,320 divided by 78 will be equal to x. Here's the arithmetic. 43 times 1,320, get my answer, divide that by 78, that's going to be x. So x here is 728 feet. Another type of relationship that's very common in physical sciences is inversely proportional relationship. In an inversely proportional relationship, the reciprocal of one variable increases, and at the same time the other variable changes by a fixed amount. So this is what a graph like that looks like. If I graph x versus y, where x and y are related inversely proportionally, the shape of the graph looks like this. It's not a straight line, and it has a changing slope down to the right. But if I were to graph the reciprocal of x versus y, so like 1 over x versus y, I'd find out that I have a straight line relationship, and that's the test to know if it's truly inversely proportional, because there are other relationships that have these kind of downward curves. Mathematically, these are almost as easy, maybe easier to work with as directly proportional relationships, and here's why. If this is true, that 1 over x compared to y is a straight line, then that means y is a slope times 1 over x. That's the equation of the line. So if I multiply both sides by x, I find that x times y is a number that doesn't change. So x1 times y1 for one point on this graph is x2 times y2 for a second point on the graph. And then I just plug in my numbers and solve for the one that I need. Proportions show up in chemistry a lot. The fixed ratios of atoms to atoms are, well, fixed ratios. So that means they're linear. And if you didn't have, in this example with water and hydrogen, any water molecules, you also wouldn't have any hydrogen atoms. So that means it's a straight line that goes through 0, 0. So that means that this ratio can be used as part of a simple proportion. So in much of chemistry, we don't have to deal with y-intercepts. We can just use the cross multiplication techniques. Let's say we had this problem to solve. The ratio of atoms of hydrogen to molecules of water is 2 to 1. So the ratio of atoms of hydrogen to 3,000 molecules of water should be 6,000 to 3,000. Cross multiplication solves this problem. Ratios of moles can be used in the same way as ratios of atoms because every mole has the same number of atoms. So the ratio of atoms to moles is fixed. So we'll find ourselves using mole ratios a lot in chemistry. Here's an example. How many moles of oxygen atoms are in 0.350 moles of aluminum sulfate formula units? Here's how I can set this up. I know that there are 12 moles of oxygen in every 1 mole of Al2SO4 3, because 4 times 3 right there. So if I have 0.350 moles of Al2SO4 3, how many oxygen moles will I have? Well, I cross multiply and divide to get my answer. Let's do the arithmetic. 0.350 times 12 divided by 1. Well, I don't have to divide by 1. I know that's going to turn out to be the same number. So this is telling me X is equal to 4.2 moles of O. Cross multiply and divide. The relationship between two linear relationships is itself linear. And this shows an interesting way that scientists can use linear relationships to describe things and make predictions about physical quantities. The conversion equation between Celsius degrees and Fahrenheit degrees. I can never remember this, but I can always recreate it. Here's how. I draw a graph in my mind, or sometimes actually on paper. I think about Celsius degrees on this axis and Fahrenheit degrees on this axis. I know that when it's 0 Celsius, it's going to be 32 Fahrenheit. And I also know that when it's 100 degrees Celsius, it's going to be 212 Fahrenheit. That's the boiling point and melting point of water in those two scales. So I have 2 points. A line goes through those 2 points like that. So the relationship between Celsius degrees and Fahrenheit degrees is a straight line. Straight lines have the form y equals mx plus b. Well, y is my Fahrenheit temperature. M is my slope. This is 180 degrees Fahrenheit. This is 100 degrees Celsius. So my slope is rise over run, 180 over 100. The x-axis is my Celsius temperature, and clearly my y-intercept is 32. Well, if I reduce 180 over 100 down, it's 18 over 10, which is 9 over 5. So the temperature in Fahrenheit is 9/5 times the Celsius temperature plus 32. That conversion that you've probably used before in science classes, all it is the equation of a straight line. So the equation of straight lines, the directly proportional relationship, and the inversely proportional relationship are very important quantities. You're going to see them over and over again, and we're going to use cross-multiplying to solve many, many kinds of problems in chemistry.